Hello, I am Gustavo Monteiro, and this video is a brief outline of our most recent paper entitled Nonlinear Shallow Water Dynamics with Odd Viscosity. This work was done in collaboration with Shriram Ganeshan. In this paper, we addressed the free surface dynamics for a shallow depth fluid with odd viscosity. In the long wavelength limit, both right and left propagating waves are described by the so-called KdV equation. The figure here represents the schematics of the problem, where h is the average depth of the fluid. In our approximation, the average depth must be much bigger than the wave amplitude, which we described by A, and much smaller than the wavelength lambda. The nonlinear dynamics is derived in a regime where all shear viscosity-induced vorticity is confined within the boundary layer, which we describe by delta here. Delta is the smallest scale of the problem, and outside the boundary layer, the flow is irrotational and can be expressed as gradient of a scalar function. The Navier-Stokes equation reduces to Bernoulli's equation at the boundary. The effective dynamics is one-dimensional and governs the time evolution of the surface profile. The effective dynamics is one-dimensional because the bulk dynamics is fully determined by the incompressibility condition. This work builds on previous of our work, where the potential approximation for the free surface dynamics with odd viscosity was derived in these two references here. The presence of odd viscosity modifies the Bernoulli equation at the surface, what gives us a different boundary condition. Starting from the potential approximation with odd viscosity, we derive the KdV equation for the free surface profile, which we represent by eta here. In the long wavelength limit, the odd viscosity terms plays the role of surface tension, however, with opposite sign for right and left movers. Here, g corresponds to the acceleration of gravity, h is the average depth of the fluid, and Niwad is the odd viscosity. Odd viscosity breaks time reversal symmetry between right and left movers. And for large values of odd viscosity, meaning when the absolute value of odd viscosity is bigger than this quantity here, this effect is more pronounced, and one of the chiral sectors becomes solitons of depression, while the other one propagates as solitons of positive amplitude. This corroborates with the idea that odd viscosity plays the same role as surface tension, however, with opposite signs for different sectors. Here in the figure, we can see the single soliton solution in this regime, where the right movers propagate with positive amplitude, and the left movers propagate as solitons of depression. This effect is exclusively nonlinear and cannot be captured within the linear approximation. In the linearized regime, the amplitude is not determined. This is a nonlinear effect.